Our understanding of food has long been dominated by calories, macronutrients, and portion sizes, but emerging research reveals that our gut bacteria interpret food in ways that are far more nuanced and arguably more influential than the simplistic labels on packaging. The human microbiome is not a passive observer. It actively metabolizes dietary components, generating a wide array of bioactive compounds that influence digestion, metabolism, inflammation, and even brain signaling. In many cases, the metabolic fate of food is determined not by its macronutrient composition alone, but by the complex interactions between dietary substrates and the trillions of microbes inhabiting the gut. This perspective challenges the notion that all calories are equal and highlights the importance of considering how plant-based, fiber-rich foods feed our microbial partners. Complex plant foods, such as legumes, whole grains, nuts, vegetables, and berries, contain fibers, resistant starches, and polyphenol that largely escape digestion in the small intestine and reach the colon intact. It is here that gut bacteria spring into action. Beneficial microbes, including Faecalibacterium prosnitziae, Roseburia, Bifidobacterium, and Lactobacillus species, ferment these substrates into short-chain fatty acids, SCFAs, such as butyrate, propionate, and acetate. These metabolites serve multiple systemic functions. Butyrate nourishes colonocytes and strengthens the intestinal barrier, propionate modulates hepatic glucose production, and acetate participates in lipid metabolism and appetite regulation. Importantly, these effects cannot be captured by calories alone. A high-fiber, plant-based food may deliver fewer digestible calories than a refined snack, but its microbial metabolites provide far-reaching health benefits that extend well beyond energy balance. Polyphenol and other bioactive compounds in plant foods further illustrate the disconnect between calorie content and physiological impact. While humans absorb only a fraction of polyphenol in the small intestine, gut bacteria metabolize the majority into phenolic acids and other compounds with antioxidant, anti-inflammatory, and signaling properties. These microbial metabolites influence metabolic pathways, immune function, and even brain health. For example, berries and nuts are rich in polyphenol that encourage the growth of SCFA-producing bacteria, while simultaneously producing bioactive metabolites that dampen oxidative stress and modulate inflammatory signaling. The same amount of sugar or carbohydrate in a refined snack does not undergo this transformative microbial processing, highlighting how the type of food can matter far more than caloric equivalents. The interaction between dietary fat and microbes is equally revealing. Monounsaturated and polyunsaturated fats from nuts and seeds, when combined with fiber and polyphenol, provide a nutrient matrix that nourishes beneficial microbes and supports microbial diversity. In contrast, saturated fats from animal sources or processed oils may encourage the growth of bile-tolerant, pro-inflammatory bacteria, reduce SCFA output, and promote systemic inflammation. Thus, even when calories are matched, the microbial interpretation of food diverges, resulting in dramatically different metabolic and inflammatory outcomes. Gut microbial responses also explain why two people can react differently to the same food. Individual variations in microbiome composition, diversity, and functional capacity mean that the same meal may produce a cascade of beneficial metabolites in one person but a less favorable profile in another. This is why personalized nutrition, informed by microbial analysis, is emerging as a powerful tool. Rather than focusing solely on calories or macronutrients, interventions can be tailored to provide substrates that specifically feed the microbes that promote SCFA production, reduce inflammation, and improve insulin sensitivity. Foods like pistachios, legumes, berries, and leafy greens are often universally beneficial because they supply a broad spectrum of fibers and polyphenol that support diverse microbial communities, enhancing the probability of favorable metabolic responses across individuals. Moreover, timing and sequence of food intake influence how microbes process dietary substrates. Evening consumption of fiber-rich snacks, such as nuts or legumes, may enhance SCFA production overnight, promoting gut barrier integrity, moderating fasting glucose, and supporting anti-inflammatory signaling by morning. The dynamic rhythm of microbial metabolism demonstrates that the health impact of a food is not static, but depends on when and how it interacts with gut bacteria. This microbial clock adds another layer of nuance that cannot be captured by calorie counting or macronutrient labeling. In practical terms, Understanding that the gut interprets food differently encourages a shift from thinking about food merely as energy to thinking about it as a tool to shape microbial function. Prioritizing complex plant foods rich in fiber, resistant starches, and polyphenol promotes SCFA production, microbial diversity, and anti-inflammatory metabolites that optimize metabolic, cardiovascular, and immune health. Simple swaps, such as replacing refined snacks with pistachios, berries, or legumes, provide substrates for beneficial microbes, reduce inflammatory signaling, and stabilize blood glucose, demonstrating how microbial mediation transforms the nutritional value of a meal. Ultimately, the gut microbiome reframes our relationship with food. Calories and macronutrient labels capture only the energy we extract directly. They miss the vast, transformative metabolic activity of our gut bacteria. By focusing on foods that nourish beneficial microbes, fiber-rich, polyphenol-dense, and plant-forward, we engage the microbiome as a partner in metabolism, inflammation control, and systemic health. The functional value of food, in this view, is determined as much by microbial interpretation as by human digestion, underscoring the importance of food quality, diversity, and timing in achieving optimal health outcomes.